So we're going to begin chapter 9, the chapter on aldehydes and ketones, with an introduction to carbonyl compounds. So chapters 9 and 10 are going to be where we focus on carbonyl-containing compounds. So the carbonyl group is it's a carbon that is doubly bonded to an oxygen, and it might be one of the most important pieces of functionality in organic chemistry. Hundreds of millions of organic compounds, natural products, contain this piece of functionality, and we use it constantly in synthesis. So there's sort of two ways to break up these carbonyl-containing compounds, and I sort of just chunked them off into two classes. It seems your book focuses on those that do not have a group, which can be displaced by a nucleophile. So those carbonyl-containing compounds which do not have a good leaving group. And this will be what we focus on in chapter 9. So these will be the aldehydes and the ketones. And then there's a whole bunch of carbonyl-containing compounds that do have a group that can either be easily displaced by a nucleophile, or, after we protonate it, we can easily displace it after the nucleophile attacks. And that'll be chapter 10. So that'll be carboxylic acids and their derivatives. And in chapter 9, we'll focus on aldehydes and ketones. But I want to sort of introduce you guys to the carbonyl group and explain a little bit about what it looks like and how it can function. And so I'm going to draw just a generic carbonyl. So it's a carbon that's doubly bonded to an oxygen. And then depending on the functional group, there'll be obviously two more bonds coming off of the carbon. In general, we've got a dipole moment going up in this direction, which puts a partially negative charge on the oxygen and a partially positive charge on the carbon. And so this particular carbon is susceptible, due to that partial positive charge, to attack by some nucleophile. And so that group right there, the carbonyl group, is what we're going to focus on in chapters 9 and 10. So this thing here, that right there is the carbonyl group. And so we know that the oxygen is more electronegative than the carbon, right? So there's this dipole where that double bond right there, those 4 shared electrons, they're not being shared evenly. The oxygen is hogging the electron density, so that puts that partial negative charge up on the oxygen. So that particular carbon is what we would call the electrophilic part of the carbonyl group. And due to that polarity, we can do a bunch of chemistry at that particular site. So there's a couple of things I should probably mention before we get going. We will often use this little R for rest of molecule, but it's usually for us to depict an alkyl group. And so I could have an R that's bonded to a carbon, which is doubly bonded to an oxygen. And then something coming off the other side, either another R group or, a hydrogen in the case of an aldehyde, which we're going to cover in this chapter. But if it's just an R group and we have some generic something or other on the other side of that carbonyl, we would have R being the alkyl group. You could also have an aryl group. So if it was an aromatic group, right, a phenyl ring or something like that, or a phenyl group, that's also fair game. But these groups right here, so these parts of this group, so the carbonyl and then whatever's bonded to the other side there, these are what we refer to as acyl group. And substituents bonded to the acyl group, right, strongly affect the reactivity of the carbonyl compound. So R can be anything, right? Starting with a carbon. It can be an alkyl group. It can be, an alkyl group with substituents attached to it. If those substituents are electron withdrawing, you can imagine the partial positive charge on that carbon is going to be bigger. If there are electron withdrawing groups somewhere on the chain near to the carbon bearing a hydrogen that's right next to the carbonyl, you can imagine that that particular hydrogen might be a little bit more acidic. We're going to take that to our advantage as we move through the chapter. But at the beginning of this chapter, I just want to introduce you to the two types of carbonyl compounds that do not have a group that can be easily displaced. And when I say they can't be easily displaced, it's not like it's not a possibility. It's just under normal circumstances, these particular groups are not going to be going anywhere. They're just a little too basic. So let me just draw a generic aldehyde and a generic ketone so you can get sort of an idea about what they look like. So with the aldehydes, we've got a carbonyl carbon, right? So we've got our generic carbonyl here with the two groups that are bonded to that carbon on either side of the carbonyl, and one of these in an aldehyde is going to be an R group or an aryl group or any kind of like carbon-containing group right over there. And then over here on the other side is just going to be a hydrogen. With a ketone, instead of that hydrogen, it's just another R group. And it doesn't have to be the same R group, right? We can use R and R prime. I'll just put two R's here, just so you know that a ketone is simply going to be a carbonyl group that is bonded to an alkyl or an aryl group on both sides of the carbonyl, whereas an aldehyde is going to be a carbonyl bonded to an alkyl or an aryl group on one side of the carbonyl and a hydrogen on the other. So we can draw these dipoles again, just like we did above. And in both of these species, we've got oxygen pulling electron density away from the carbon. It puts a partial negative charge on both of these oxygens and a partial positive charge on the carbon, part of the carbonyl. So we remember we were talking earlier about the ability of alkyl groups to stabilize a partial positive or a full-on positive charge with a carbocation anyway. And we were talking about how the primary carbocations are less stable than or more reactive than the secondary carbocations, and those are more reactive or less stable than tertiary carbocations. And that was due to the ability of those p electrons in those alkyl groups, those carbons that are right next door, to hyperconjugate, right? And hydrogen doesn't have p electrons. So then, therefore, that leads us to believe that these are just a wee bit more reactive than a ketone, because in a ketone, that partial positive charge can be stabilized by through hyperconjugation. Because the hydrogen has no p electrons, to help stabilize the partial positive charge. On the carbonyl carbon. So that makes that particular carbon just a little bit more reactive. And so these groups right here, when I was saying these particular carbonyl compounds have groups, right, that cannot be easily displaced by a nucleophile, I'm talking about these right here. These particular groups here cannot be easily displaced by a nucleophile because when they leave, if they were to leave, so these groups are not easily displaced. So they're not good leaving groups. Because if they did, they would be too basic. And we know that really basic groups make poor leaving groups, right? What do I mean by that? So first of all, they would be, if they did leave, a hydride anion so what is that? That's hydrogen, right? With an extra electron and a negative charge. Or, in the case of the alkyl group, some carbanion. And very generically, we can just do R with some electrons and a negative charge. And what do I mean by that? Well, if you were to look at the conjugate acid of these guys, the pKa of hydrogen, right, is somewhere around 40. And the pKa of some alkyl group is somewhere around 50. So the hydride anion and some carbanion, right, is going to be pretty wildly basic. So they're not taking off. H minus is not leaving, and some carbanion is not going to leave, right, under normal circumstances. It's not like a halide is taking off, right, or we're going to protonate a hydroxyl group and water is taking off. Nothing like that. This would be some carbanion, wildly basic thing, or the hydride anion would be taking off. So these particular groups, you can attack them with a nucleophile, but R minus or H minus are not taking off. We can add to aldehydes and ketones, and we'll talk about that later on when we do reactions with these guys. But for the most part, you can add, or you can deprotonate alpha to the carbonyl. There's all kinds of chemistry that you can do with aldehydes and ketones, but simply just displacing one of those groups is not going to be one of them. So let's just get started and learn how to name these things. They can be a little weird. I'm going to do aldehydes first. And often, when we're naming aldehydes, either you can use the IUPAC system, right? So it's the systematic nomenclature where we're simply just going to take, again, our parent hydrocarbons. So remember way back in, I think it was chapter 2, we were going over alkanes, and I said we're going to fly through some of these rules. I'm going to give you a whole bunch of them in this chapter because they're really going to apply as we move forward with the other functional groups. This will be another situation where you're going to be finding out what the parent hydrocarbon is, or was anyways, and you're going to, in the name, drop the E at the end of whatever the alkane was, right? And then add an al at the end. Your carbonyl carbon is always going to be your first carbon. And for common nomenclature with aldehydes is pretty common for small aldehydes. And by small, I mean aldehydes that contain 6 carbons or less. Typically, we use the common name for the carboxylic acid, which I'm going to give to you guys now. We haven't covered carboxylic acids yet, so there's no way that you could know this. So I'm going to introduce just the first 6 common carboxylic acids, and I'm going to sort of explain their etymology. For that, we're going to end up dropping the ic acid at the end of that name and just adding the word aldehyde. So let's give a few examples here. With the number of carbons, and I'm just going to start with the smallest number of carbons and work our way up. So for 1 carbon, the structure of that particular carboxylic acid, so this is all, roll it all back to methane, right? Just 1 carbon, right? 4 valence electrons. And so with that, we're going to take our carbon, begin with your carbonyl, because all these are going to have a carbonyl. And with an aldehyde, remember on the right over there, we had just a hydrogen. With a ketone, we had some other R group. With a carboxylic acid, we have a hydroxyl group. That's what differentiates these from each other. Remember in chapter 1 when we had you guys learn all the functional groups? Okay, so with this particular carboxylic acid, having only 1 carbon, the only thing that can be on the other side is a hydrogen to complete the octet, right? So the name of this particular carboxylic acid is formic acid. The IUPAC nomenclature would be methanoic acid, right? Meth meaning one carbon, but formic acid is the common name. Formic acid is the acid that is generated by fire ants. So if you ever get bit by a fire ant and it burns, that's formic acid. And the word formica is Latin for ant. So these common names, so these smaller carboxylic acids, the common names come from common things, right? So these names were given a very long time ago when these compounds were figured out to be from a common natural source. And so they were often named using either Latin or Greek wording. So if you have two carbons, now I can start here again with my carboxylic acid. The thing that makes it a carboxylic acid is that. What's hanging off the other side? Well, it looks like one more carbon, right? Because this one's going to have two. So it'll be a methyl group, right? So this thing right here is called acetic acid. That's the common name. The IUPAC name would be ethanoic acid. So you can kind of see a pattern here, right? Eth is 2, meth is 1, prop is 3. We're going to do that all the way through with the IUPAC nomenclature, but the common nomenclature, acetic acid, is nothing that you could guess, right? You'd have to know it. So this is like something you have to see the structure, you have to know this is acetic acid, right, for the common nomenclature. This is such a common carboxylic acid that most often people refer to this as acetic acid instead of ethanoic acid, but either is fine. Here we're just going through the common nomenclature. Where does this word come from? Well, vinegar is made up of 5 to 6% acetic acid. The smell that you smell of vinegar, right? Vinegar is a solution, right? A homogeneous solution, but it contains acetic acid as one of the solutes, right? So acetum is the Latin word for vinegar. So that's where that comes from. If you've got 3 carbons, this one's a little weird, right? So the name anyways, I think. So 3 carbons. There we have it, right? The carboxylic acid portion of it. This is propionic acid. This is Greek, actually, instead of Latin. Pro means first and pion means fat. So propionic acid means first fat. Not exactly the most exciting meaning in the world, but propionic acid is is the smallest of the carboxylic acids that displays fatty acid properties. And so it was named the first fat. It's the smallest fat. So this one's not very exciting in terms of nomenclature, but that's the common name for carboxylic acid with 3 carbons. This next one with 4 carbons, so the whole thing has 4 carbons. This is butyric acid. This smell of this stuff could peel the paint off the walls. I'm not making this up. If you've ever smelled rotten butter, that's butyric acid. And it comes from the Latin word for butter. Rancid butter is loaded with butyric acid, and it smells like 800 kinds of hell. It's horrible, but that's where it gets its common name. So this would actually be butanoic acid for IUPAC nomenclature, but butyric acid is the common name. If we have 5 carbons, this one's kind of nice. It actually, the smell of this is not all that great either, but it's kind of nice where it comes from. The word anyways. So we'll get our carbons out here. 1, 2, 3, 4, 5. Okay. This is valeric acid. It's kind of stinky, but it's kind of sweet where it gets its name. So valerian, you've heard of valerian root, right? Is a flower that contains valeric acid. So, hundreds of years ago when they come up with these structures and they have to name it after something, it's probably going to be named after, the natural product in which it was found. And so valeric acid is found in large quantities in a flower produced by the valerian plant. If you've never heard of valerian root, you can find it in a health food store. They sell valerian root for helping people go to sleep. It's just one of those little herbal supplements that you can take. It's supposed to make you tired. And so the last one for the common nomenclature, because we stick to the smaller, shorter carbon chains, I'm going to give myself some space here. So there's 6 carbons in this one. Is that 5 right there? Yeah, and then the 6th one is the carboxylic acid. This is caproic acid. Any of you work on a farm with goats? The smell of a goat, that's caproic acid. Caper means goat. So that's where it gets that name. Okay, so those are the common names for the carboxylic acids. We'll cover carboxylic acids in chapter 10, but I wanted to share these common names with you because there's no good way to teach you how to give the common name for a smaller aldehyde, and the smaller aldehydes typically do go by their common names. So there's really no good way to teach you about that without sharing these carboxylic acids with you. This will only make chapter 10 that much easier because we've pretty much covered the first part of the nomenclature for those. But let's go through some examples. I want to show you how to give the common name for some of these aldehydes as well as the IUPAC name. And so that very first one right there has 2 carbons. So the common name for that, if we looked up at the top here, we see this is acetic. It comes from acetic acid, right? Was the carboxylic acid, but with 2 carbons being the aldehyde, this is, and I'm sure you've heard of this word before, instead of acetic acid, we have acetaldehyde. So when your liver oxidizes ethanol, when you have like a glass of wine or a beer or something, this is the first step. Acetic acid is the last step, but acetaldehyde is sort of like that in-between oxidation state. It's responsible for making you feel like total crap the next day, this particular molecule right here. The IUPAC nomenclature would be just a little bit different, right? So we would be naming this after the parent hydrocarbon, dropping the E, right? So instead of ethane, because that would have been ethane, right? 2 carbons. We're just going to drop the E and add Al. So this would be ethanal. But again, this is one of those really small aldehydes. And so these small aldehydes typically go by their common name. The next one has, how many carbons do we see? 1, 2, 3, 4. And so instead of butyric acid, right, we're going to take the common name from the carboxylic acid and we're going to turn it into the name for the aldehyde. We drop the ic acid and add the word aldehyde. So instead of butyric acid, this would be butyraldehyde. And the IUPAC nomenclature for that would be, well, if we had 4 carbons in the parent chain, it would have been a butane, right? So we're dropping the E. We're going to add al. So this is butanal. So what about this next one? This next one has a substituent on it, doesn't it? Now, we just did a chapter on alcohols, and you're probably sitting there going, well, when we did that chapter, we named the compound for the functional group. And you're right, and we're still going to do that. But here, I'm going to tell you the aldehyde of the 2 possible functional groups there, right? We have the hydroxyl group, which could have made this an alcohol, and then we have the aldehyde functionality there, which makes it an aldehyde. Which one of those takes priority? So there's a list. There's like a hierarchy for these things. I'm going to share that with you in a bit. For right now, just naming this thing, 2 things I want to mention. First, the aldehyde is going to take priority. The second carbon after the carbonyl, because the carbonyl is going to be the first carbon, that second carbon, when we do common nomenclature, doesn't take a number, but we have to indicate that the hydroxyl group is on that carbon and not, say, the third one, right? And so with common nomenclature, they don't use numbers like we do with IUPAC nomenclature. They use lowercase Greek letters. The very first carbon after the carbonyl, so technically the second carbon in the chain, right, is called the alpha carbon. And so this is called alpha. And when that hydroxyl group is not, when we're not naming this as an alcohol, but when we're naming the hydroxyl group as a substituent, it's a hydroxy group. So this is alpha hydroxy. And now we're just going to name the aldehyde as usual, right? And this is the common nomenclature. So this is a derivative of propionic acid. So we're going to drop the ic acid and add aldehyde, right? So it's propionaldehyde. With IUPAC nomenclature, we use numbers. So instead of alpha hydroxy, this will be 2-hydroxy. And this has 3 carbons, so that's prop. It would have been a propane, but it's an aldehyde. So we're going to drop the E and add al. This is propanal. Why is that carbon 2? Because the carbonyl carbon is carbon 1. So that hydroxy group is on the second carbon. If it's common nomenclature, it's on the alpha carbon. The alpha carbon, that hydrogen sitting there on that alpha carbon is something we're going to talk about a lot toward the end of this chapter. That's a big deal, hydrogen over there. So we're going to get to know our common nomenclature pretty well with these. I want to give us some more practice with these little lowercase Greek letters. In case you're not familiar with the system, I'm going to label these carbons. So the very first carbon in our aldehyde is going to be the carbonyl carbon. And so the carbon, the second carbon in the chain, the one right next to the carbonyl carbon, instead of using a 2, right, for IUPAC nomenclature, with common nomenclature, with these smaller aldehydes, 6 carbons or less, we're going to use lowercase Greek letters. So this very first carbon here is the alpha carbon. That's the alpha position. The third carbon, or the second one away from the carbonyl, is the beta carbon. So I can write these over here. This is alpha. Then we have beta. And this one over here is gamma. The next one out is delta. So that's that's the symbol we use for our partial positive and partial negative charges, right? That little lowercase. That's a delta. And this last one out here is epsilon. Okay. So when we're naming these things in the common nomenclature, we don't use numbers like we do in the IUPAC system. So if I'm going to name, say, for example, that first one down there, and also not even just small aldehydes, but also aromatic aldehydes. So if you've got like a phenyl ring, right, or like an aldehyde that has a phenyl substituent, we're also going to use common nomenclature for that. This first one over here on the left, I've got 4 carbons. So this is some kind of, instead of butyric acid, right, it's a butyraldehyde. And then on the beta carbon, we have a chloro group. So I have to write that down. If it was IUPAC, it would have been carbon 3, right? But this is the beta carbon, so this is beta chloro. And then we have to name this for the parent. So this would have been butyric acid if it was a carboxylic acid. It would have been butane if it was an alkane, but it's an aldehyde. So using common nomenclature, we're going to take the common carboxylic acid name, and we're going to drop the ic acid and add aldehyde. So this was butyraldehyde. Beta-chloro-butyraldehyde. This over here has its own common name here. So we've got a little benzene ring, and this is going to be having the aldehyde directly attached to the phenyl ring. This is benzaldehyde. It would have been benzoic acid, but we're dropping the ic acid. That's the common name, right? For that carboxylic acid. We're dropping the ic acid and we're just adding the word aldehyde. That is benzaldehyde. And by the way, talking about the smell of things, that particular compound smells like little Italian Christmas cookies. It's delicious. Well, it smells delicious. It smells a little bit like amaretto in a way, like amaretto and flowers. Okay, so moving on to the next one. So not all of these things stink, just saying. So moving on to the next one, we've got 5 carbons. And it's an aldehyde. So this is some kind, with the common nomenclature anyways, it's a derivative of valeric acid. So this would be a valeraldehyde, right? And that little NH2 right there, that's a group that we haven't covered just yet. We talked a little bit about them. That's our amino group. And that's going to be on the, let's see, there's alpha, beta, gamma. It's on the gamma carbon. So we've got gamma, amino. So when it's not an amine, right, when the NH2 is actually a group, a substituent, it's the amino group. And this is going to be on what? So the parent here is valeraldehyde. So if this was IUPAC nomenclature, that would have been on the 1, 2, 3. That would have been on 1, 2, 3, 4, actually. 1, 2, how many carbons are here? 1, 2, 3, 4, 5. Yep. 2, 3, 4. It's on the 4th carbon. So it would have been 4 amino pentanal. But with common nomenclature, this is gamma amino valeraldehyde. So I just gave a couple of examples where we're talking about functional groups, or we're talking about compounds where there is more than one functional group on the molecule. In the last example where we had the alpha hydroxy propionaldehyde, and this very last example I just did with the gamma amino valeraldehyde, we're looking at a compound that has 2 functional groups, the aldehyde and some other functionality. And so we've got to share with you, I have to share with you anyways, a list of how to prioritize these particular functional groups. Just like we had priorities with the RS nomenclature, we're going to have priorities when we're naming compounds that have more than one functional group. So you're not, in this class, we've been keeping it simple and just teaching you how to name a molecule that is simply just an aldehyde, or if there's a substituent, it's like we're telling you how to name the carbon that it's on. But very often in natural products, there's going to be a whole gang of functional groups. Definitely more than 2. on a lot of these functional groups. And so we have to have a way to name these compounds, which functional group is actually going to be in charge of the nomenclature, as in what functional group is going to take priority. So I have this little list that I wrote down for you. And I can probably put this on some sort of like a sheet. I don't expect you to memorize this. After you've named a few of these, this sort of becomes second nature. But I made a list going from top priority to bottom priority or lowest priority for everything I could think of that I could possibly ask you with a molecule with multiple functional groups in this class anyway. And the very top of the list is going to be the carboxylic acid. So if you're going to name this thing for the carboxylic acid, the suffix is going to just be oic acid or ic acid. If for whatever reason the carboxylic acid is not taking priority, say there's 2 carboxylic acids on the molecule, right? And they're in different spots, and you want to name one over the other is going to be part of some substituent, then the prefix for a carboxylic acid that is a substituent would be the carboxy group. Carboxy, whatever the substituent is. A derivative of a carboxylic acid would be an ester, and we'll cover those in chapter 10, but if it's going to be named for the ester, O8 is going to be the suffix. If the ester is being named as part of a substituent, it's going to be whatever that alkoxy-carbonyl group is going to be. Alkoxy meaning like you're going to have to be specific about the number of carbons, but alkoxy meaning it's some sort of carbon-containing ester functionality as part of the substituent. The amide group, simply just named it for the amide, right? So whatever, or amide, some people call them amides. The amido group would be the prefix for that. A nitrile would be next, right? So that carbon triply bonded to a nitrogen, that's next on the list in terms of priority. Those things would be named as the nitrile. And if they were a substituent, it would be the cyano group from the cyanide anion. We have 2 different possibilities for an aldehyde, and that's going to be next. Notice how aldehyde takes priority over ketone. So if you've got a molecule that's got a ketone functionality and aldehyde functionality, it's going to be named for the aldehyde. In both cases, the suffix is al, but if you've got a terminal aldehyde, so for a terminal aldehyde, if it's going to be named, say for example you have an ester that has aldehyde functionality, and the aldehyde functionality is on the end of the chain, right? Then we're going to use the prefix oxo to designate that oxygen in the carbonyl of the aldehyde. That is the substituent. I will give examples of this. The other way that we could name an aldehyde is if it was part of a substituent. So if that substituent C is bonded to the rest of the group here, so this bond right here hooks it up to the rest of the molecule, and that whole carbonyl with the hydrogen is part of the substituent, then the word formal or the prefix formal is used to indicate that there's an aldehyde there. Ketones come after aldehydes in terms of priority. One, like acetone, for example, is the suffix that we will use. And if the ketone is a substituent, so it's part of another molecule, it's part of a molecule that has another functional group that actually takes priority over the ketone, then the oxygen we would designate as an oxo group. Alcohols come next, and that's why we named that aldehyde as an aldehyde, and we used hydroxy to designate that the alcohol, the hydroxyl group, is a substituent. Amines, so that NH2 group that we just talked about, when I named it for the aldehyde and said the amino group is going to be the prefix, right, for the substituent. So those come next. Then we have our alkyl groups. The alkene comes first, then the alkyne, then the alkane. And those suffixes we already know. Alkenyl, alkynyl, and alkanyl are going to be the prefixes for those. And again, the alk part of it is going to depend on how many carbons you have. And then there's, last but not least, we've got our ethers and our alkyl halides. There aren't any suffixes for these. The alkoxy group can be used to designate the ether group as a substituent, and halo is going to be the prefix that we use to designate an alkyl halide as a substituent. So let's give some examples of this. It's easy to run down a list, but it doesn't make a lot of sense until you see it in action. So I've got a couple of molecules here with multiple functional groups, or at least in both of these examples, I've given an aldehyde as a piece of functionality along with another functional group. And if you look back at the list, you see in that first example, now you have to go back to chapter, I think it was 1, where we asked you to learn the functional groups. And we were talking about esters being where we have the carbonyl, and then we have an oxygen, but instead of a hydrogen, where it would be a carboxylic acid, we have some other kind of R group. That's what makes it an ester. So this piece right here makes it an ester. This piece right here makes it an aldehyde. And on our list of priorities, we saw that the ester takes priority over the aldehyde. So this whole molecule is going to be named as an ester. So what we'll do then, now we haven't named esters yet because we haven't done chapter 10, so I'm just going to go ahead and tell you that we're going to name the group over here on the ester first as its own word. So this right here would be a methyl group. And then we're going to count over, and for this we're going to use some numbers here. So that carbon right there for the ester, that carbonyl is going to be carbon 1. Then there's carbon 2, 3, 4, right? So on the 4th carbon, you see, so that methyl group's off by itself. There's no dash after it separating that from the 4, right? Ester's a little weird. So we're going to name the methyl group, and then we're going to begin with the rest of the molecules. So on the 4th carbon, we have some aldehyde functionality. It's not the star of the show. It's a substituent. And what is it though? It's a terminal aldehyde. It's on the end, right? So we're going to use the prefix oxo for that. So we've got, let's see, I think it's the 5th carbon. Let me count them again. 1, 2, 3, 4, 5. Yep, it's the 5th carbon. Because the oxo group, we're talking about the oxygen. And that's on the 5th carbon. So oxo, and then there's 5 total carbons. So pent, instead of pentane, it'll be pentanoate. Let me break this all down. So here we've got O8, which means it's an ester. Pent means there's 5 carbons, so 5 total carbons. Oxo means I have a terminal aldehyde, and it's on the 5th carbon. The oxo group is on the 5th carbon, right? So the aldehyde contains the carbon, right? The oxygen and the hydrogen, but the oxo group is talking about the oxygen. And then methyl over here, this is the group on the ester. In the next example, we've got an aldehyde, piece of aldehyde functionality. So here's the aldehyde. And then up here, remember from chapter 1, we have an amide. Some people will call it an amide. No big deal. What is a big deal? That the amide or the amide takes priority over the aldehyde. So that thing's got, let's see, 1, 2, 3, 4, 5, 6. So that's going to be some sort of hexane derivative, right? And it's going to be an amide. So instead of hexane, it's going to be hexanamide, right? Because that's going to be the suffix we use. And on, let's see, carbon, let's see, there's 1, 2, 3, 4, 5, 6 carbons. So on the fourth carbon there, what do you see? You see the aldehyde, and it's a substituent. See how it's now a CHO instead of just the double bond O? So we're referring to this group now as a substituent. And so we're going to use the prefix formal. It's not an oxo, it's a formal, right? Because we're referring to the CHO group, not just the oxygen part of the carbonyl. So how do we start this out? Well, on the fourth carbon, we have a formal group. And we have 6 carbons total. Was a hexane, drop the E and add the word amide, or amide, and however it's easier to say. For formal hexanamide. So we can break this apart. We've got an aldehyde as a substituent. And this is going to be on the fourth carbon. We've got 6 total carbons in the whole molecule, and it's an amide. So that's probably as bad as it's going to get in this class in terms of nomenclature, where you've got 2 or more functional groups. You just have to refer to that list so that you can prioritize your groups. So the last couple of examples here I want to give for the aldehydes are, obviously we can have a ring, right? So if we're going to have a ring, that's going to be our parent compound. If the ring is attached to an aldehyde, then you're simply just going to add the word carbaldehyde to the name of the cyclic compound. And so one thing that's important to note is that the carbon bearing the aldehyde, so in the ring here, this carbon bearing the aldehyde is carbon 1. And so when you're naming this thing, you don't, if it's just got, the aldehyde on it and nothing else, you don't have to write 1. It's implied. If you've got something else on the ring, you're going to start counting from that carbon. So you're not going to start counting from the aldehyde, like the carbonyl carbon. You're going to start counting from the carbon in the ring that bears the aldehyde. This first one is pretty simple, right? That's a cyclohexane. That's the parent. And then we're just going to add the word carbaldehyde. To the end of it. Because that's carbon 1, right? So this is carbon 1. This has to be carbon 2. It could have been carbon 6, but we want to give our substituents the lowest possible number. And we're stuck with that carbon 1 being carbon 1 because it bears the aldehyde. It's got higher priority over the halogen. So we're going to name this 2-bromo cyclohexane carbaldehyde. Again, you don't have to put a 1 in there. The 1 is implied because the aldehyde is attached to the ring, and we're naming it after the cyclohexane. So moving on, I would like to cover the nomenclature for ketones. Ketones are a little weird. It's usually only a few ketones, I should say, use common nomenclature. We've got another type of nomenclature called derived nomenclature, and it's a little reminiscent of ethers, where you would name, you know how like in an ether you've got like two R groups on either side of the oxygen. In a ketone you have the carbonyl functionality, and then you have two R groups on either side of the carbonyl. So you can kind of think of it like the nomenclature for the derived naming can be a little bit like that, where you're going to name each of the alkyl groups separately in alphabetical order, and then you're just going to follow it up with the word ketone. Remember how we did that with ethers? Common nomenclature, same old thing. You're just going to take, for the little ones, you're going to take the common name from a carboxylic acid. You're going to drop the ic acid at the end and just add -one. For example, acetone, right? IUPAC is probably the easiest. And we're simply just going to remove the E from the parent hydrocarbon. And this can be nice because with IUPAC nomenclature, we can use the numbers. Now with a ketone, you know, that carbonyl can be anywhere in the chain. So it's nice that you can say it's on carbon 4 or it's on carbon 3 or whatever. So we're going to drop the E from the parent hydrocarbon and add -one to the end. And because the carbonyl doesn't have to be on the second carbon, it can be anywhere, we're going to make sure that when we're numbering the chain, when you find your longest continuous chain, the carbonyl is going to get the smallest possible number in that chain. So let's do a few examples. So starting off with this little one down here, it's got 3 carbons. The carbonyl is in the middle, so it's on the second carbon, right? So that's going to matter for IUPAC nomenclature. With common nomenclature, we're going back to the common name for the carboxylic acid that would have, in this particular case, 2 carbons, right? And then the R group off to the other side is just simply a substituent. So this common name would have been named after acetic acid. We're dropping the ic acid and we're adding -one. So it can't be a ketone, right, if there's no R group on the other side. So we're going to look at the carbonyl, and then the easiest thing to do is to go, you know, find your longest continuous chain that contains the carbonyl, and then whatever other group is hanging off the other side, that's just like, you know, your R group, kind of like with ethers. So we're going to name this after the common name for the carboxylic acid with 2 carbons, because that's our longest continuous chain that contains the carbonyl functionality from the carboxylic acid derivative. So instead of acetic acid, we have acetone. For the IUPAC nomenclature, we have to let you know where the carbonyl is. There's 3 carbons. And honestly, with 3 carbons, you can't have a ketone if the carbonyl is anywhere but where it is, right? Because if it was on either of the other carbons, you would have had an aldehyde, right? But we're going to say that this is 2, so on carbon 2. And again, it can't be a ketone if it's on carbon 1, or I guess if you're counting from the other direction, carbon 3, right? But giving it the smallest possible number, we're telling you it's on that middle carbon, it's on carbon 2, and that's propanone. But again, propanone is fine too, right? Because it wouldn't be a ketone if the carbonyl was elsewhere. The derived name is simply, I'm going to find the carbonyl and I'm going to look at the groups on either side of it. I see 2 methyl groups, so I have a dimethyl ketone. Now for these other groups, for these other molecules, not always do you actually have a common or a derived name. Like for example, this next one, there is no common name, right? Nothing that can adequately tell you where that carbonyl is, right? That thing's got 1, 2, 3, 4, 5, 6, 7 carbons. We're not really into using common names past, say, 6 carbons. There's a few, like some of the fatty acids have, you know, their own common names. But for this one, no common name. We're going to use an IUPAC name, though, to let you know that I can count from either direction. I can either go from left to right, where that carbonyl falls on carbon number 3, or if I counted from right to left, it would be on 1, 2, 3, 4, 5, right, on the 5th carbon. So we want to give it the smallest possible number. So we're going to tell you that this is 3 because that's where we find the carbonyl. And then there's 1, 2, 3, 4, 5, 6, 7 carbons total. So that's a heptane derivative. But it's a ketone, so we drop the E and add -one. So it's 3-heptanone. For the derived nomenclature, I'm going to find the carbonyl, and I'm going to look at the groups on either side of it, just like I did with the ether. So I've got an ethyl group on the left, and a 1, 2, 3, 4, a butyl group on the right. In alphabetical order, it would be butyl, ethyl, and then ketone. And for the last example, we've got IUPAC only. And sort of IUPAC and common, right? Because these cyclic compounds, they share. So this right here is going to be named after the cyclohexane, but we're going to drop the E and add -one. So this is cyclohexanone. And we don't have a derived name because you get the same groups in either direction and they're all tied together in a ring. So it's simply cyclohexanone. Okay, so let's move on and name a few phenyl substituted ketones. So these are our little aromatics. These typically go by common names. And when we're using the common name, we're going to take the common name of the carboxylic acid derivative and we're going to sub the word ophenone in for ic acid as a suffix. And with the derived names are nice because it's like an ether, right? You find the carbonyl and you just look at the groups on either side of it. So if I start out with derived name, I see a phenyl group on the left for this first molecule, and I see a methyl group on the right, but we're going to put them in alphabetical order. So this would be methyl, phenyl, ketone. The phenyl group is a substituent, so it's not a benzene, right? This is named after the ketone, so the phenyl group is a substituent. So methyl phenyl ketone. The common name for this, right, because it's a ketone and it's going to have 2 carbons, so this is acetic acid derivative, see the CH3 and the carbonyl right there. And then to indicate, right, that this is got a phenyl substituent on it, we're going to put ophenone instead of ic acid. So instead of acetic acid, right, what do we have? We have acetophenone. For the second example, the common nomenclature, this would be named after the common name for the carboxylic acid. So imagine that instead of one of those phenyl groups, we had an OH. So if you have a phenyl substituent, right, and it's going to be bearing the carboxylic acid functionality, right, so we just have a benzene ring with a carboxylic acid on it, nothing else. It's a benzoic acid, but the derivative, the aldehyde derivative, or I'm sorry, the ketone derivative of that with a phenyl substituent would be benzophenone. So instead of benzoic acid, benzophenone. And the derived name is pretty simple, right? It's just diphenylketone. So, just like the aldehyde can have more than one functional group, your ketone can too. And so you have to decide what takes priority. So back on that list, we were talking about compounds, and we had them listed in terms of priority. So we've got this first molecule. What do you see? You see ketone functionality and you see aldehyde functionality. And so where do I see that? Well, here's the aldehyde. So this is the aldehyde functionality. And then this right here, R, carbonyl R, is the ketone. We saw on that particular chart that aldehydes take priority over ketones, right? So this is going to be named for the aldehyde, but we have to let you know where the ketone is. And that oxygen is special, right? That carbonyl oxygen. So we're naming for the ketone nomenclature as a substituent is going to be the oxo group. And where is it? It's hanging out on, so we're going to start counting the carbons from carbon 1, right? That's carbon 1, 2, 3. As we're counting the chain, right? So we see that we have the oxo group on carbon 4. So we've got 4. That ketone oxygen, right? That's our oxo group. We have 5 total carbons in our aldehyde, like our longest continuous chain, right? So we've got a pent something. It was what? Pentanal. Okay. And so for the next one, what do I see? I see a ketone. And check this out, you guys. Either direction you go, you get the same number for the carbonyl, for the ketone. So this right here, no matter what you do, 1, 2, 3, 4, 1, 2, 3, 4, it's always on the 4th carbon. There's our ketone. Right here, this is an alcohol, right? But the ketone is going to take priority over the alcohol, and so this is going to end up being a hydroxy group, and we're going to name this for the ketone, right? So then what are we going to do? We're going to number our chain. We can go in either direction. If we go in from left to right, the ketone ends up on the 4th carbon, right? Or the carbonyl is in the middle there, and it's the same number if we go from right to left. So if we go from right to left, the hydroxyl group actually gets the lower number, so we're going to go from right to left. That puts the hydroxyl group on the 2nd carbon, and we have to call it a hydroxy group, because we're naming this for the ketone, and the hydroxyl group is a substituent, so it's a hydroxy group. So 2-hydroxy, and then we have to let you know where the carbonyl is. We know it's a ketone, but either way, it's on the 4th carbon, right? The carbonyl. And the whole thing has 1, 2, 3, 4, 5, 6, 7 carbons, so this is a heptanone. The "-one" tells you that the thing is being named after a ketone. Hepta means there's 7 carbons in the parent. 4 is telling you where you spotted the ketone, where you found that carbonyl. And hydroxy means that you've got a hydroxyl group as a substituent on the 2nd carbon. This is what's great about IUPAC nomenclature. You can't mess it up. When you read the name from right to left, it's like you can just decorate the whole thing. With common nomenclature, it's like, okay, what? Valoraldehyde. How many carbons was that? You know what I mean? And they're common because they're common, right? So they're found in natural products, and some of them are commonly used, like, acetic acid or whatever, or acetone, very common solvent. But with IUPAC nomenclature, it's like you can't mess up drawing the structure, because it basically tells you where everything is and every little feature about the molecule. All right, let's do a couple more. And then we'll call it a day for the nomenclature. And after this, we'll get into the reactivity of these guys. It's the fun part about this chapter anyway. I see 2 ketones. Now what do you do? This is the next one, right? So there's 2 ketones. Great. So I see one here. How do you know what to call this thing? I see one here and I see one here. So these are both ketones. But when we have cyclic compounds, right, we're going to name that as our parent. So this is going to be some kind of what? Cyclohexanone. So that means that this whole thing is a substituent, isn't it? So now we got to get creative with this. We know that if we're going to name this thing for the cyclohexanone, we know this has to be carbon 1, right? Because it's the carbon that bears the functionality. And so we can count clockwise or counterclockwise. If we count clockwise, this is carbon 2. If we counted counterclockwise, that would have been carbon 6. So we're going to stick with carbon 2, right? Because that gives the lower number. It gives your substituent priority. So now remember, with IUPAC nomenclature, it's kind of like you stepped off into another planet now. We're on our own, like this, it's like its own molecule, but it's a substituent. So I'm going to count the number of carbons that are actually in the substituent. So I've got, let me use a different color for that. I've got 1, 2, 3, 4, 5. And so I've got some kind of pentyl group, but on that pentyl group, on the third carbon, I have an oxo group, right? That's the oxygen of the ketone functionality. That is a part of the substituent. The whole thing is a substituent. It's a pentyl group, but on the third carbon of the pentyl group, I find the ketone, and it's an oxo. That oxygen is special, right? It's the oxygen of the carbonyl. But the parent of this thing is going to be the cyclohexanone. So where do I see that substituent? I see it on the second carbon. And then remember, in parentheses, I'm going to say, here's the substituent inside the parentheses. On the third carbon of the pentyl group, I find an oxo, right? That's that double bond oxygen for the ketone. Part of the pentyl group. And then cyclohexanone. If the pentane was the derivative, right, it would have been pentanone, but it's a pentyl group. So you have to say, okay, what makes that ketone part of that substituent? Well, first I have to find out where the carbonyl is. It's on the third carbon, right, counting away from the parent. There's 5 carbons total. I see the carbonyl on the third carbon. That oxygen is going to be referred to as an oxo group. So that's all in parentheses. It's an oxopentyl group, but where's the oxo? On the third carbon of the pentyl group, right? Where's the whole thing on the cyclohexanone? On carbon 2. So this is what's really great about IUPAC nomenclature. Okay, last example. I've got, let's see, just a ketone, and I've got 2 alkyl substituents. Those are near the bottom of the list, right? So we know we're naming this for the ketone. We also know that we're going to give our ketone functionality the lowest possible number. And so this has to be counted from right to left, right? So I've got 1, 2, 3, 4. Some kind of butanone, right? And on the third carbon, so don't get confused and think on the third carbon you have 3 methyl groups. Remember, your parent is going to be your longest continuous chain. Our longest continuous chain is 4 carbons, and so there's technically 2 methyl groups on the third carbon. Does that make sense? Sometimes it's easy to just be like, I see you over there, T-butyl group, right? But we're actually giving this the name for the ketone, and we're looking for the longest continuous chain. So this is a butanone, but it has 2 substituents. So we've got 3, 3 dimethyl two, which is sort of redundant in a way, because where else could that carbonyl be and still be a ketone? Butanone. So if the carbonyl was on the 4th carbon, it would be an aldehyde, right? And if the carbonyl was on the 1st carbon, it would be an aldehyde. It can't be on the 3rd carbon because the 3rd carbon's busy being bonded to 4 things already. So we've got that on the 2nd carbon. It can't help but be on the 2nd carbon, but you can put the 2 in there. It's a little redundant, but it's okay. All right, so that's going to do it for the nomenclature part of this. In the next lecture, I want to start talking about the reactivity. I think I'm going to break that into a couple of chunks, and I'll get working on those notes tomorrow. But I'll post this right now to YouTube.